Okay, so basically today is just going to be a bit of a look on Kimberlites, Lamproites, and then the impact of some of the geological features on the sampling and the resource aspect of these bodies. Just in very brief sort of overview quickly, on the Kimberlite side, just the key features of this rock type, some of the family and the varieties that you can find in Kimberlites, shapes, pipe zones, textures, and then of course, how do they in place and how do you classify them? A quick detour into the Lamproites, a little bit less detailed, but just some of the key features that are typical of Lamproites. And then of course, I mean, Kimberlites are volcanoes after all, so you need to understand a little bit about the volcanic processes to make sense of what's happening in the pipe and in the crater. Then just a very quick little bit on resource sampling, mainly for the young geologists that are attending. And then how do you pull it all together in terms of the geology, the geostats, and other properties that can actually assist you in compiling and constructing a fairly robust resource model. So in terms of basics, a kimberlite really is a fairly volatile rich, so CO2 rich, potassic, and an ultra basic rock, and it is characterized by a pretty low viscosity in general. So low silica obviously equals low viscosity. Being ultramafic, it's highly prone to alteration. And of course, as a result, partly of that, extra crater deposits such as lavas, etc., are rare. They do exist. We'll look at some examples, but they're generally rare. Because there are no current kimberlites erupting and haven't been for some time, there are no new examples to go on. We're completely dependent on looking at modern analogs in terms of volcanism to understand how kimberlites actually form in terms of the eruptive processes. They are the deepest known melts, so pretty special in that sense. And also because of that, difficult to reproduce experimentally. You'll appreciate that something that comes from 150 kilometers down will show quite a bit of modification before it actually eventually reaches the surface. And that is also quite problematic in terms of reproducing these magmas in a laboratory setting. They are part of a large group of related rocks, which we'll look at in a minute. And the majority of those are actually non-diamondiferous, which makes it a bit difficult. So you find them quite often during prospecting, but the really diamondiferous ones are not that common. And of course, to distinguish the kimberlites from some of the other rock types that are closely related to it, you need chemistry and some petrographic work sometimes to do that. This is a fairly old diagram, but I still, like it. It was published by Scott Smith in '95. And basically what you're seeing here is a group of curves. The height of the curve is basically proportional to the frequency with which these rock types are encountered in prospecting. So right in the center there in red, you've got your group 1 kimberlites. Next to it, the group 2s, then the lamproites. And then on either side, left and right, you've got a sac name known as melnites. So that would include things like alnites, melilitites, polsonites, etc. So they are basically going more towards your ultramafic lamprophire suite. And then on the other side, the monettes, calc-alkaline lamprophires, and similarly moving away from the kimberlites. And of course, the depth of melt separation then gets shallower. And then you'll notice that in the middle, these curves sort of overlap over here. And basically that is due to the sharing of some of the properties of the rocks. You get things known as K1Ms, which have some overlap in terms of properties between melnites and kimberlites. The same, you get phlogopite-rich group 1s, and then the same happens between group 2s and lamproites, etc. In terms of kimberlites, there are really the two main types, group 1, and they are characterized by fairly depleted, isotope geochemistry, and then the group 2s, which are your micaceous kimberlites, and they've variably been known as micaceous, orangites, and lately, after some work by Pearson et al. In 2019, have been termed carbonate-rich olivine lamproites. Some examples of these types of kimberlites, the group 2s, that is, would be things like Finch, Voorspoed, Lace, Swartruggens, and then Roberts Victor. Those are just some of the common ones, or the better known ones in South Africa. As I've mentioned, isotopically distinct and phlogopite dominant in the case of the group 2s. The isotope signature definitely very much more enriched. If you look on these diagrams over here, you'll see these sort of rocks trending away. So those, the lamproites in sort of the light blue, and then the orangites or the group 2s in orange color there. So enriched signatures to the bottom and to the bottom right in terms of isotope space. So geochemically, higher potassium titanium, light rare earth enriched, and higher in barium typically compared to the K1s. And then, of course, there are some very close mineralogical, compositional, and as I mentioned, isotope similarities to the lamproites. They're also higher in CO2 and calcite compared to the lamproites, and hence the name that Pearson et al. Suggested for them, which, by the way, was, I think, proposed originally by Barry Dawson in the 80s already, that that these rocks are actually closer allied to lamproites than the kimberlites. So if we look at the kimberlite shapes, just simply looking in the southern African region, it's evident that there is a vast array of different kimberlite shapes and forms. And it's quite clear when you look at these different morphologies that the emplacement process is actually quite diverse. There are a number of factors which impact the shape of a kimberlite pipe, not least of which, of course, is the country rock geology, but also things like the magma rheology, the water content or availability of water, volume of magma, etc. So in this diagram, you can see basically your typical Orapa style pipe on the right-hand side, more of a Johann type with coherent or pyroclastic kimberlite in the central part of the pipe, with or without crater basins. And then you have your coherent only kimberlite craters, and then on the right-hand side, volcanic clastic only, and sometimes even just very small vents, and then things like blind domes and so forth. So if we go to the root zones now, so starting in the kimberlite pipe from the bottom upwards, on the left-hand side, you'll see some sections and plan views from the Wesselton pipe in Kimberley, and on the right-hand side from De Beers pipe. You'll notice immediately the very irregular shapes of these plan views. That is because the kimberlite at these levels basically have to use joints and fractures to propagate its way upwards, and therefore it does not represent such a smooth morphology as in the upper zones of the pipe. You can see here, for example, the W7 at Wesselton, a blind dome. It emplaced and it didn't get any further than, as you can see here, at about 600 level on the maps. If we have a look at the rocks from this region, basically very dark. This is typically an uncontaminated sort of kimberlite on the top left-hand image, aphanitic on the left-hand side of the sample, macrocrystic kimberlite, and of course macrocrystic basically just being a non-genetic term referring to these anhedral large olivine insets, typically 0.5 to 5 millimeters in size. They usually refer to olivine, but they can refer to any mantle mineral, garnets, clinopyroxenes, orthopyroxenes, and of course even diamond, which of course if it's crystallized in the mantle, it's xenocryst in the kimberlite. Top right, thin section view. Of course, olivine crystallizes as a primary phase in kimberlite magma. So you see there the phenocrysts. And for comparison, in terms of size, there's a macrocryst on the left-hand side with the very fine-grained ground mass. Bottom right-hand side, also some examples of macrocrystic kimberlite. If you look carefully, dike within a dike, you can see there's the contact defining a dike in the middle, which is characterized by coarser olivine macrocrysts, finer on the edges over here. And then an example of a hypabyssal kimberlite, and this shows one of the other typical features of hypabyssal or magmatic kimberlite, and that is the thermally altered country rock fragments that you see in these type of rocks. These are all basement gneisses that you can see here, these white sort of blobs. They've been quite heavily altered. Up at the top left here is a shale or a mudstone, which also shows a thermal alteration pattern on it. Moving now to the diatreme zone, and for that we move up to the north of South Africa on the border with Zimbabwe. The Venetia pipe or cluster, essentially four main pipes and a whole lot of smaller plugs and dikes, all of which give or take 500 million years old. They are intruded obviously in the central zone of the Limpopo mobile belt, so very high-grade metamorphics for the wall rock that it intruded into. And these rocks basically range from purely magmatic through to pyroclastic and also some reworked volcaniclastic material. But basically the reason for this particular example is to show you the diatreme zone facies, or the rocks which are found in them. And these are some examples of very, very typical diatreme facies, Kimberlite. So this occupies the sort of the central zone of the carrot, if you like. You'll notice the rock is very well mixed. It's pretty homogeneous looking. And you'll also see that the country rock fragments that you can see in here are actually fairly pristine. They are not very thermally altered. There's one example here, which is a little bit of a halo. And also on the photograph on the right-hand side, you'll see that all of these fragments are still fairly fresh. In terms of the mesostasis or the ground mass, a primary pyroclastic rock typically contains between 20 and 30% porosity. So all of that space has been infilled here with hydrothermal products, things like serpentine, saponite or magnesium-rich clays, chlorite, brucite, etc. These are the dominant minerals that have been analyzed from this ground mass. You'll notice also that it is actually quite difficult to detect pyroclasts in this rock. You don't really see them. The reason for that is largely because they are very thin rim, usually in the diatreme zone. So they are extremely difficult to spot. Under thin section, of course, under a microscope, it's a different story. You'll see them very clearly, but in hand specimen, they are quite difficult to identify. But every now and again, you'll find some rocks where you see some really spectacular features, and it leaves you in no doubt that the rock is actually volcanic and more specifically pyroclastic. You can see here the very, very prominent pyroclasts. These are all altered basement clasts or basement clasts. They're not that altered. You can still see amphibole and biotite in that one. And then the brownish sort of rim from the pyroclast around it. So unfortunately, very seldom this spectacular, usually quite a struggle to see those pyroclasts. And then if we move up onto the crater, this is the geologically most complex part of the actual kimberlite, and in fact for many volcanoes, for the simple reason that you have in this area of the pipe, you have a combination of both primary pyroclastic as well as volcanosedimentary deposits. And all of these actually behave differently with respect to diamonds, and indeed the processes that form them are actually quite divergent. So what you're looking at here at the top left, this is the Orapa kimberlite pipe in north central Botswana. Dual pipe or double pipe system. There you can see the north pipe over there, southern larger pipe to the south, and you'll notice that the south postdates the north. It has truncated the top of the north pipe. And in here in the south, a complex array of volcanosedimentary as well as pyroclastic sequences overlaying the more straightforward sort of pyroclastic successions at the bottom. And then just for comparison, over on the top right-hand side, there is an olivine malilitite crater. This particular one is Lolmurwak, which is in the Lake Natron Ingaruka monogenetic volcanic field in the north central part of Tanzania. And for comparison, there is a scoria cone, so a Mar crater on top, scoria cone on the bottom, and you'll notice the sort of lopsided view of this scoria cone. It's because the wind was blowing from right to left at the time of eruption, and it deposited the bulk of the ejecta on the one side of the pipe, very little on the right-hand side, most of it on the left. So the complexities not only inside the crater, but also in the extra crater tuffering material, depending on weather conditions, volume of magma, violence of the eruption, and direction of the blast, you can have very, very different looking craters in close proximity to each other. Another example of the variability that is evident in a crater, this particular sequence of photographs were taken between June 2007 and June 2008, and is from the Aldonialengai carbonatite, or the crater thereof. And you'll notice that you go from a crater that is almost totally filled and showing various little hornitos and individual little vents inside it, to, after a fairly catastrophic eruption, a huge hole in the top of the mountain, and everything blown out, and basically a totally different environment. So this is within the space of only 12 months, and things can be very, very fluid in a crater environment. And of course, bear in mind that what you eventually observe when you drill your kimberlite is the last phase of eruption, or the last sequence of activity that took place. And you basically have to decipher what happened prior to that. This particular example is a pipe in East Java. This is Rahung stratovolcano as it looked in 2015. The reason for this photo is just to illustrate that you get a complete transition in many volcanoes, and kimberlites are no exception. Here you had a very violent caldera eruption. The crater is 2 kilometers across. That was followed by a period of quiescence, and basically the floor of the crater filled up with a lava lake, as you can see over here. And then it resumed explosive activity, slightly less violent. There's a double scoria cone in the background there, and the rear vent is active, the front one dormant. So this combination of quiescence and explosive activity is something that you also see in kimberlites. Dominantly explosive in the case of kimberlites, but lava lakes do occur, and we'll look at some examples in a bit. So moving on to the emplacement and the classification of kimberlites. There are both mineralogical and textual classification systems in use or available, and have been published and written about. The mineralogical classification dates back to the late 70s, Skinner and Clement, and was largely based on the main groundmass minerals. But the primary nature thereof was quite a contentious issue. Initially in that paper, minerals such as serpentine and calcite were deemed to be primary. Experimental work has since shown that minerals such as serpentine can't be stable above much beyond 300 degrees, which would effectively make it a hydrothermal type mineral. But nonetheless, minerals such as monticelite, phlogopite, etc., those are very much primary. In terms of the textual classification systems, there's a whole plethora of papers and work done since the late 70s all the way up to very recent. Right, there we are. So basically, we said that there's ongoing debate around the kimberlite emplacement, and as a result of that uncertainty, there's a lot of different and diverging opinions on some of these classification techniques. There are basically two main emplacement models, the magmatic versus the phreatomagmatic, and we'll have a look at each of them individually quickly, just to set the scene. However, before we get there, essentially kimberlites are really volcanoes. So one of the preferences that I have is simply to stick to a volcanic and a volcanosedimentary system, which is commonly known and is understood by scientists the world over in terms of these when you classify or when you describe your rocks. And so these are basically the systems that we're currently using in De Beers on the operations to actually log and to map the kimberlites. So in terms of the magmatic model, it's basically pertains to a sudden release of a magmatic vapor and gas system. So in other words, it's gas driven, and it usually relates to a decompression effect close to surface, and as the magma ascends through the subcontinental lithosphere. There's basically the eruption is dry. There's no interaction with groundwater, unlike with the phreatomagmatic model. Dawson introduced the concept of fluidization, which did not remain entirely consistent over the years. The definition of what fluidization actually involves did change somewhat over the years. for example, in the case of Clement, who advanced the model further with the concepts of the embryonic pipe formation, fluidization basically refers to the upward, or sorry, the downward movement of a degassing front into the pipe, whereas Sparks basically views fluidization as the upward flow of gas through the pile of the ejector. And the most recent work on this, on the magmatic front, basically was the 4-stage model by Sparks in 2006. On the right-hand side, starting with the stage 1, you have a narrow conduit, typically a fissure or a small pipe. When the eruption commences, of course, there's an overpressure situation. Material is ejected from the system, and the eruption continues. But with time, obviously, particularly the upper parts of the crater become unstable, it becomes broken, it collapses inwards, and of course, in doing so, the vent widens and the pressure then decreases. Once this process carries on even further, at the point where the pressure of the eruption is equivalent to that of the atmosphere, internal deposition now becomes possible in the vent. Fluidization processes may be active as well. And usually from that point onwards, particularly large, coarse blocks, etc., big particles are no longer able to be ejected from the vent, and the vent may in fact become choked off at the bottom, depending on the stability of the wall rocks, etc. And then, of course, the last phase of this particular model is then the hydrothermal alteration, which then pervasively flows through the pile of ejector from the source of heat at the bottom. And then, of course, this model of emplacement is unlikely to be a once-off bang. It usually, with any volcanic system, or the period of activity is usually measured in at the very least weeks and mostly months and years. Moving on to the phreatomagmatic model. This is a very common process across many magma types, not just kimberlite, but it extends all the way through to andesites, dacites, and is a very, very commonly seen emplacement mechanism in volcanism. And it basically involves the ascent of magma and then interacting with groundwater, either in fractures or in aquifers, etc. In doing so, it usually produces fairly violent explosivity, as you can imagine, when a hot magma comes into contact with cold water. The diagram on the bottom left-hand side basically gives you an indication of how this works. So there you've had your column of magma rising, you intersect the groundwater, and you generate an explosion. And then one of two things can happen. You can either use up the groundwater, in which case the scenario is very similar to a well being overdrawn. And of course, as the cone of depression develops in terms of the water table, the point of explosion moves further and further downwards, and thereby deepening the crater. I should also add that the explosion or this explosivity only happens very close to surface. Anywhere below 300 meters, usually you cannot produce an explosion due to the high confining pressure. So this is very much a process happening near the Earth's surface. If water supply is abundant and exceeds the rate of supply of magma, then all you do basically is generate a bigger and bigger crater in the ground, but remaining more or less at the same elevation. So you generate something that looks a bit like a champagne glass or a soup bowl, rather than a steep-sided vent system. And of course, with all the water around, you can imagine that the alteration of the volcanic ejecta is going to be quite substantial over short periods of time. One of the recent or last advances over the last couple of years have been the fact that there's been observations in some of the work and vent systems that have been studied, that once the diatreme has been established, depending on the level of water, and for example, if there's significant amounts of rain, water may percolate down and you may end up having magma ascend to higher levels in the pipe again. And this process basically leads to the formation of tephra or debris jets. Of course, if this process reaches the surface, you'll generate another little vent inside the bigger original diatreme. If not, then what you will do basically is just develop a region of highly disturbed and disrupted volcanic products down in the actual vent itself. Some of these features have been observed in Kimberlite, and there's potential examples of it here. This particular photo on the left was taken in Arapa in the North Pipe. And there you can see the contact of one of these vents running down on the left-hand side is the one edge, and the other contact on the right-hand side over here with a adult for scale in front. You can see it's quite a few meters across. Very poorly sorted. You can see the large boulders inside of it. And then the photograph on the right-hand side, this particular example was taken in the early days at Volcanic, circa 1984. And you can see the little funnel-like structure here extending over about 3 different benches. So for scale, a bench is about 12 meters here, give or take. So you can see more or less the size of these little vents. And on the left-hand side, just the same picture that you saw just now, but I zoom in on the actual contact position. You can see the host over on the left-hand side, poorly sorted. There's the contact running just to the right of these wet areas, and then the material to the right, a lot finer grained. You'll notice down here some slump and joint structures also evident here. Then in terms of some real examples, one always sees these perfectly drawn cartoons in papers on what diatremes and vents look like. But if we go to the south of Japan, there's a little island in the Philippine Sea where there's a volcano known as Miyakijima. Now in 2000, this volcano erupted catastrophically and blew a large caldera in the island. But prior to that, there was a series of phreatomagmatic maars that actually occupied the island. And this caldera basically truncated one of these maars in a perfect section view. And this is what you can see over here on the right-hand side. So on the top there, you can see the lake, the old crater lake, the crater lake deposits just below it, the central sort of vent area, highly disrupted, poorly or unbedded material, in fact. And then on the edges here, more sort of gradually dipping angle of repose, sort of sorted and layered and bedded units. Down here at the bottom, you can see an example of a slumped piece of the wall rock, the so-called floating reefs in Kimberlite. You can see the offset there on this white unit. And note the small size of the feeder zone, the feeder dike down here, and there the actual vent starts. So a really spectacular example of a real diatreme. So a lamproite is really a per-alkaline, ultrapotassic, and perpotassic rock. The definition of a lamproite, the one important thing is that it cannot be done based on the modal mineralogy only. Textures are quite important, and compositions in particular are fairly essential. Because of the large number of liquidus phases and because these are small degree partial melts, there's considerable mineralogical diversity in these rocks, and also in the greater sort of lamprophile suite outside of lamproites and kimberlites. It's important to note also that leucite is not an essential mineral in lamproite definition, but it is most definitely characterizing. So in terms of definition or classification rather, the work by Scott Smith and Skinner in the 80s basically provided a very good system for subdividing these rocks. So you can start from a olivine rare leucite rich variety, moving all the way across into an olivine abundant leucite poor or absent rock. And of course, there are some very key characteristics associated with these mineralogical changes. First of all, your diamoniferous varieties are only found in group 3s, where these are your deeper magmas in terms of within the lamproite group itself. And then the other thing is the morphological presentation of these lamproites. Your group 1s, being more siliceous, tend to be preserved as positive relief features, whereas your group 3s, being more mafic and more prone to weathering, generally tends to be weather as negative features. And if you look at the mineralogy very quickly, on the left-hand side, these are the typical minerals that you find in a group 1 and to a degree group 2, with the exception of multicellite. Ground mass on the right-hand side, these are the minerals that you see in a lamproite. You'll notice there are some that also occur in both the perovskite, the apatite, etc. But note that the compositions are actually quite distinct. The apatite in the lamproite is very fluorine-rich, strontium, barium. Same for perovskite. The amphiboles are very titanium-rich. The phlogopite compositions are also different. So although the minerals are showing the same, compositionally they're very much different. In lamproites, thus far, it definitely is the case that your pyroclastic or your volcanic plastic deposits do carry higher diamond grades than the magmatic lamproite varieties. And then the last couple of points, very important to note that if there are more sodic minerals present in the rock, then it is unlikely to be a lamproite. So things like plagioclase disqualify it. Minerals such as melilite, monticellite, calcillite, nepheline, any of these feldspathoids, etc., would disqualify the rock from being a lamproite. And then things like these iron and titanium-rich garnets, also diagnostic of other rock types rather than lamproites. In terms of the morphology, top left-hand side, this is basically Ellendale, and you can see Ellendale 6. This is a group 3 lamproite. These ridges, by the way, are the country rock geology. This is not the lamproite. The lamproite is sitting in between here. You'll notice it's completely flat. There's no topographic expression. Contrast that to a lucite lamproite, Mount Weld on the right-hand side, and you'll see a nice little hill with the magmatic lamproite sitting in the middle as a sort of a lava lake. And then lastly, just bottom left to note, this is Argyle. As with Kimberlite, you can most definitely also find multi-vent complexes, the same as Kimberlites. These are also volcanoes, so in terms of the volcanological characteristics, there's no reason that they won't also show some of these features. Moving on to some volcanic processes. As we said earlier, there are no current volcanic eruptions going that would represent a Kimberlite. So therefore, we have to look at analogs in modern volcanism to understand how a Kimberlite would have been placed. The historic emplacement models for Kimberlite are largely based on or have focused on end-member volcanic processes. So in other words, for example, a gaseous eruption would, for example, rather be focused around airfall and maybe some pyroclastic flow type processes. The phreatomagmatic model, on the other hand, would encompass processes such as pyroclastic surge, also with a bit of airfall. But it's worth remembering that in volcanoes generally, there are 3 key processes that always occur regardless of magma composition, and that would be the airfall, your pyroclastic surge, and your pyroclastic flow. The other point to note is that these never occur in isolation, or very, very seldom. They are always mixed. For example, airfall will always occur with surge and with flow. So these processes cannot be divorced from each other. They do occur together. And I think that has led to a lot of the initial debate and arguments regarding the emplacement of Kimberlites as well. So let's just have a look at kimberlitic lavas. We mentioned early on that they are very rare, but if we go to the central western part of Tanzania, northwestern part of Tanzania, there's a kimberlite known as Igwisi Hills, a very young kimberlite, by the way, less than about 12,000 years old. A triple vent complex, Mar crater on the top right-hand side, and then 2 scoria cones. But what is significant about this particular occurrence, apart from its age, its very young age, is that there were copious kimberlitic lavas produced here. The Mar vent actually overflowed and produced a lava flow to the northeast. And similarly, there were lava lakes in the 2 tephra cones or scoria cones to the southwest. So the system youngs in age from northeast to southwest, and this is one of the best preserved examples of kimberlitic lava flow. And here on the right-hand side, you can see a section through this lava flow. You can see the very vesicular top of the flow over here, and then moving downwards, you'll see it becoming progressively enriched in olivines. That's these black looking shapes over here, and in thin section there, you can see the olivines, and then the vesicles, the more irregular vesicles up at the top of the flow. And then just for comparison, over on the left-hand side, this is a carbonatitic lava from Aldonia lengai. It literally flows like water, and you tend to form these very, very thin little almost pancake layers of these lavas. So if you alter this, take it for a few million years, alter it, you'd be forgiven for thinking that it might be quite well bedded pyroclastics. Another example over here, if you have a little sample here in isolation, looks very lava-like, maybe even segregationary hyperbissal. But this points to the hazards of actually looking at a sample out of context, because when you look at the full sample, you will actually see that it is a pile of compacted and sintered pyroclasts in a volcanic package. So what you were looking at initially was the bottom part of this unit. As you move upwards, you can start seeing the individual pyroclasts with the ash in between it. So very, very important to always refer to the geology adjacent to a sample that you collect in order to get the full picture. So if we look at airfall processes, these are some of the very distinct features that you can see for an airfall deposit. First of all, on the top left-hand diagram, very well sorted in this particular case, quite clearly class supported, some thin surges in between as well. Your airfall deposits typically mantle the topography, they drape, and you can see a very homogeneous sort of layer of class supported pyroclastics over here in the top right-hand image. Depending on weather conditions, you can find very extreme sorting of airfall deposits. This is Krakatoa or Anna-Krakatoa erupting, very strong wind blowing, and you'll notice the airfall deposits being deposited downwind from the vent. And of course, the sorting will take place as well. As you move further away, you'll be going smaller and smaller in grain size. Basically, moving on to the pyroclastic flows. So these are essentially very high density gas solid surface flows which run down the side of a mountain. They are gravity controlled, essentially very, very destructive and capable of carrying a considerable load of debris. This bottom right-hand example is a flow from St. Helens. You can see the amount of debris in this particular flow, and also the neat contact where it actually stopped. That is typical of these sort of features. They usually form either from a column collapse or from a lava dome collapse, which of course is not relevant in kimberlites, but definitely from column collapse. And you do see these features in kimberlites. Here is an example. If you look at unit 2 on the left-hand side here, this is a pyroclastic flow deposit that was mapped in the south crater of Arapa. Fumarolic structures, high temperatures, and this was confirmed through some temperature and magnetic work that was done on these lithologies. It was definitely a hot event emplaced or surrounded by volcanosedimentary units above and below. So indication that the vent was still fairly active late-ish in its life. Pyroclastic surge. These features are basically a more gas-rich equivalent. They carry a lesser load in terms of denser material, but in doing so, they're also able to travel a lot further, also across water. The top of a pyroclastic flow can detach and form a surge, which may head off entirely in its own direction, depending on the topography. These typically form either as lateral blasts from a vent in phreatomagmatic conditions. As you can see over here, a little valley coming down from the crater filled with these pyroclastic surge deposits. And accretionary lapilli, as you can see in the bottom left-hand side, which are essentially pyroclasts coated by ash. These are totally diagnostic of these pyroclastic surge deposits. Usually because of the presence of steam and electrostatic charges, you get ash wrapping around the rims of these pyroclasts. They're very delicate though, and they get easily destroyed. We see these in kimberlites as well. Bottom left is an example of a surge in Voorspoed. This is an example of some low angle crossbeds in surges from Johann. And here is another rotated block from the tuff ring which fell into the crater. You can see the very prominent bedded units in there. Some thoughts on resource sampling. The one thing, of course, is that confidence in a resource does not come cheap. And also there is, particularly for the new geologists or the guys who are now thinking of starting a career in geology, there's no thinking out the box when it comes to sampling. There's no quick and easy or thumbsuck or any shortcut to the sampling process. You unfortunately, if you want to do the job properly, you need the data, and therefore the sampling has to be done. It's expensive, of course, and so nobody likes to do it, least of all the accountants. The other point to note is that when you consider sampling, the variogram of that particular deposit, which I'll talk about in a second, should govern your sampling. So you actually need to take some samples so you can construct a variogram before you even start your main sampling campaign. So in terms of estimation, a valid estimate for individual blocks can only be obtained when your variogram range exceeds the resource block size that you pick and your sample spacing by a generous margin on a defined drilling grid. Another thing that people love to do is to actually use delineation holes for resource definition. Preferably it should be done on a previously optimized drill grid. Leave the delineation holes for the geology work. And the unfortunate thing about sampling is that if your sampling campaign is inferior, you will not realize it, because you will still get grade estimates and you'll still be able to populate your blocks. However, unfortunately, the confidence on those numbers will be very much less than what you were hoping for, even in the type 1 or the long-term block models. So if we just briefly look at a sampling campaign, just some theoretical holes in blue over here, the relationship, the statistical relationship and spatial relationship between these samples are defined by what is known as a variogram, and that is simply a relation of the variance over distance between the samples. So these points over here are basically the sample pairs that you're plotting as a function of distance. And one of the very important features of a variogram is this point here, the so-called range, because at this point, you move from correlated statistics into uncorrelated or random statistics. And that has a very, very big impact on sampling and the reliability of your samples. So let's, for argument's sake, let's say you decide to remove some samples from your carefully optimized grid. You can see that by removing the yellow samples and also the orange samples, if you were to remove these holes, you would remove much of your correlated statistics in your drill grid. And you would essentially be having a spacing that is uncorrelated. So in other words, the red samples don't talk to the blue samples at all. And that has a very big impact in terms of confidence for a block estimate. And not only do you lose that correlated statistics between the holes, but you also then, of course, lose the information of the holes themselves that you've taken out. So there's a double whammy. It's the holes that you've removed, but you've also degraded your entire sampling campaign. So this is definitely worth keeping in mind for those going into economic geology. So then on to the last section, just pulling the whole lot together. What is possible in terms of the various techniques. In terms of resource risk, what is the degree of the internal geological variation that you're dealing with? Is your deposit looking like the example on the left? Is that the geology that you're seeing? Is it very complicated over small distances? Or is it like the example on the right? Is it fairly monotonous and massive? And then, of course, what causes this variability? Is Is it volcanosedimentary processes? Are they pyroclastic processes? And how could this impact your diamond grade? It's important to identify the major geological units which impact your diamond grade and revenue. It's easy to get carried away looking at all the textural and visual differences in these volcanic rocks, which are very abundant and very common because, I mean, the crater is a very heterogeneous and very violent system, and it produces a lot of textural heterogeneity. But it is important to focus on the actual differences that impact your grade and your financial parameters in the resource model. And one of the best ways to do that would be to look at chemistry. These are just some examples of ground mass spinel plots, pulling apart various magma signatures in different pipes. This is Koffiefontein, Voorspoed down at the bottom. That was a Victor in Canada that we heard about earlier. And so through some careful analytical work, one can go some way in supporting the modeling decisions made. Most of your geological parameters are also regionalized variables, things like dilution, rock density, rock strength, dense media separation yield, etc. So once you can show that a variable is regionalized and there's a spatial structure to it, you can then, of course, also estimate it through processes like kriging, or you can simulate it through conditional simulations. And that allows you to move to a different level in terms of risk definition. You can then create block models from these parameters, and that could be an additional input into your mine planning process in terms of either treatability, rock strength, or whatever the case might be. You can also generate from this, of course, probabilistic models. Here is an example of the probability of your UCS, your rock strength exceeding 40 MPa per individual block. Down at the bottom there is DMS yield, another block estimate of a metallurgical parameter. Then, of course, probabilistic methods can also be used to simulate your actual pipe volume, and then also plan your drilling according to a maximum reduction on variance that you can get from these sorts of exercises. Similar type of techniques, so stochastic uncertainty principles, etc., can be applied to your diamond size distributions and valuations. There's been some work done on that and published that you can go and have a look at. And then in conclusion, so as you've seen, both kimberlites and lamproites are part of a complex and quite variable group of rocks, very few of which are diamondiferous, and therein lies the rub, and the ability to recognize what is a true kimberlite as opposed to a malnoite or some parakimberlitic variety is quite important. As you would have seen and hopefully realized from this presentation, your kimberlites are essentially governed by the same processes as in any other volcano. They are volcanoes themselves. The magma composition is very, very unique, but the actual volcanic processes are no different to any other volcano. And so, of course, keep an open mind, because no two vent systems are ever exactly identical. They do have their own personality, each one of them. It's important to corroborate your visual geology with analytical techniques. Your textural and your visual features do not tell the full story, and in fact sometimes overcomplicate your geology, as for reasons I've just mentioned. The textures, one tends to be naturally drawn to the visually different in the geology, but that does not always correlate with what is economically sensible. The geological units that you do define must be accurately portrayed in terms of key resource parameters. So principal of those would be diamond grade, diamond revenue, dilution, and your ore treatability. Those four would be the paramount characterizing features that you should try and build into your resource model. And then, of course, a range of uncertainty is always better than a single value in terms of confidence and quantification of risk. And then, particularly for those of you, the young guys interested in going into economic geology, try and be proactive in your use of geology. Try and alert the operation or the mine to future ore treatment problems, grade changes, etc., rather than explaining it after the event. A very common theme that something happens and then one has to try and explain it afterwards. Whereas with a little bit of work and foresight, you know, you could have alerted operations to it. And then after your geological definition, just to close off with, of course, your next most important thing is an appropriately optimized sampling campaign. That is probably the single biggest area of downfall where prospects and projects have failed in the past. And that, I think, brings me to the end, other than to just alert you to a new paper coming out soon by authored by Mike and myself and a couple of other people. Look out for it. It should be available pretty soon. Thank you. Apologies for the delays halfway through.
That was a very comprehensive talk, and particularly for people who may be just entering into the world of diamonds and kimberlites, it's worth reviewing this every once in a while. The geological complexity is significant in many kimberlites in many provinces. There's probably time for one comment or question. If anybody would like to raise their hand or just unmute themselves. There's a couple questions in the chat box. Is it possible to determine the rate of emplacement for kimberlite facies?
Yeah, I'd have to think about that a little bit. Look, I mean, the rate of emplacement depends to a large degree on the volume of magma available. And then, of course, the difficulty in which the magma has to find a path to the surface. Generally speaking, volcanoes or the magmas do ascend very quickly. I mean, if they didn't, then there wouldn't be much left of the diamonds because they do suffer quite a bit in the actual kimberlite magma. So the ascent is pretty rapid. In terms of the actual volcanic emplacement, once you get to surface, that would be entirely, or not entirely, but significantly controlled by the conditions encountered close to surface. So in other words, is there water? Is it high-grade metamorphic rock, or is it soft mudstone that it has to emplace into? Yeah, and then I see there's another part of that question. Does olivine abundance have any relation to diamonds? Yes and no. The amount of juvenile material in the kimberlite does have a rough correlation with prospectivity, if we can call it that. But remember that olivine doesn't only occur inside of the diamond stability field. At shallower levels in your graphite stability field, you also have olivine-bearing rocks. And these olivines would be added to the load as the kimberlite passes through. So to take a count of your olivine and to try and equate that to a grade is a little bit hazardous because there are barren areas, of course, that you will be passing through where you will be sampling olivine, but which may carry no diamonds. So yeah, it's not as straightforward as you know, a simple correlation between the olivine, but obviously the more diluted the rock is with country rock fragments, the lower the grade potentially could be. And of course, I mean, olivine in itself is also a dilutant. Of course, for every olivine crystal, you know, you take space away where you could have had a diamond.
Yeah, it's an interesting one though, Johann. I mean, you were aware that generally, you know, when we looked at kimberlites, if you saw lots of good macrocrystallic stuff and plenty of you know, good garnets, you always got excited about them. And I think there's that story, and I think it was at Letseng, where in the early days, you know, if they wanted to get to the better grade or high grade kimberlite, they'd give guys a tin and go and count garnets across the pipe.
Yeah, no, look, there is that, John, you're quite right. Really speaking, the more juvenile material you have,
yeah,
you know, the better chances are. But it's not as, I know that there's been some work done in the past looking at olivine sizes, even, you know, as a correlation between olivine size distribution and diamond size distribution. But it's very tenuous. It may work in some instances, but it depends also which facies you're looking at, etc. I don't, it's not a technique, you know, in all honesty. I would far rather sample for the actual diamonds than to try and to decipher the olivines. You know, once you've done the correlations, you've taken the diamond samples and you've counted the olivines in them, you could maybe make some pronunciations on that, but I think not without any diamond samples.